Next, we're going to look at 1.3, which is about the network core, and we're going to talk about how the routers in the core kind of actually do the switching and how they actually create this internal network structure. All right, so this kind of basic question, how is data transferred through the network? There are two very broad answers to this question. They are circuit switching and packet switching. This is a very fundamental question. In circuit switching, there is a dedicated circuit for every connection between between communicating party A and communicating party B, between the sender and the receiver. In packet switching, however, all the data is chunked. It's divided into these discrete chunks of data, and those chunks make it through the network basically independent of each other. There's not a reservation that happens on the front end to make this long-standing connection. We just send it and hope that each person along the way, each router along the way, can continue sending it in the right direction. All right, so circuit switching is an end-to-end kind of process. In circuit switching, we're concerned with finding a complete end-to-end connection between sender and receiver and making sure that all of those resources along the way are reserved so that any information that's passed between them can definitely quickly be transferred. So the word reservation is really important here because that's basically how circuit switching works, is that we are reserving some resources all along this path so that when either the sender or the receiver wants to send, when they want to communicate, there's definitely resources there to communicate. Maybe this reminds you of something. I think you've used a system that's like this, right? And that's the telephone system, right? And that's why in circuit switch networks, you kind of refer to a transmission as a call, right? So when you call somebody, you're expecting for the duration of that call to be able to have this kind of sustained transmission speed so that you guys can both talk to each other. So that voice information can be sent in either direction and you can hear each other. If you started a call and later on the call quality goes down, or you can't hear every other second because the speed along that intermediate route is slower, then you would not enjoy that call, right? That conversation would really degrade. So this is circuit switching. We're going to reserve the speed ahead of time. You can kind of imagine, have you seen any of those old-timey movies where there's a lady at a switchboard who's connecting this hole with this hole? And basically, in doing that in a very manual way, they were actually physically creating a circuit between a caller and a callee, right? And that means nobody else can use those holes along the path, right? That line is taken, right? That's a circuit switched kind of network. Let's see how we would implement that in a kind of more digital world. These are two simple access techniques for sharing a medium. One is frequency division multiplexing, FDM. In this case, the idea is, right, basically, how can we create this one, how can we split this into multiple channels? You're familiar with this because you've used a radio, like in your car. You know, a radio, not an iPod, but like an actual radio. And you tune in to 107.7 star FM. And what you're doing is you're saying, only get me the signal that's coming at this particular frequency. Imagine in this case we have 4 users. We can divide our frequency width into 4 different pieces, and we would allow each one of those users to communicate, to send at a certain frequency. And we can separate them out by tuning into a certain filter, tuning into a certain frequency. Another way of achieving this circuit switch behavior is through time division multiplexing, TDM. In TDM, we divide the whole media in time slices. So in this case, we divide it like so. So you can imagine we let, imagine that each time slot is half a second long, say. So that means that user 1, the blue guy, gets to talk for half a second. And then the green guy talks for half a second, and then the yellow guy for half a second, and then purple guy, or fuchsia for half a second. And then we go back and do that whole thing again. So we're switching everybody out. This fairly divides the channel into these sub-channels, I guess we could say. And by doing this, we're able to reserve then some piece of the channel for each user. So we can make calls in this way, right, and say we've established a connection between two users and they get to use this frequency that represented by blue. They're guaranteed to be able to use that. All right, let's go through this example. How long does it take to send a file that's 640,000 bits from host A to host B over a circuit switch network? We're going to assume that all links run at a speed of 1.536 megabits per second. Each link uses TDM, that time division multiplexing, with 24 slots per second, and it takes 500 milliseconds to create that end-to-end circuit. Right, so how long does it take to send this complete file over this, this circuit switched system? Right, so how would we attack this problem? All right, so the TDM is like what we talked about before, where in time we're slicing this into 24 slots every second. So there's 24 slots in each second. How many slots does this communication get to use? This transfer between host A and host B. I'll give you a hint. It's a number between 0 and 2. All right, so you with me? So you get one slot. That's your slot. Just like before, we had the different colors in each time slot, and we'll come around. So effectively then, how many bits per second can we send? All right, do you see the waste that's going on here? What if this is the only communication going on right now? Then we waste all those other 23 time slots, right? We just sit there and do nothing. We have a link that's 1.536 megs where we're using a 24th of that speed. All right, so that's kind of the disadvantage to circuit switching when you're in a lightly loaded environment. All right, so in opposition to that, on the other side is packet switching. Packet switching says, we're going to break all the data into chunks, maybe of a certain size. And we're going to send those packets, and we're just going to send them and let them go. We're not going to reserve a circuit ahead of time. Hopefully there'll be enough capacity in the network for them to be forwarded throughout the network. And at each of those links, we're going to send it at the full speed. We're not going to divide the medium into channels. We're going to use the full speed every time. Can you think of some advantages of this approach? Packet switching.
Not reserving extra space.
Right, we avoid that. What do you mean by reservation or bandwidth?
With the previous example, if you've got 24 slots and you're only using one of them,
Yes.
that's inefficient with packets. You can avoid having to reserve those other 23 slots.
Mm-hmm. Actually, if we can go back, we didn't completely finish this problem. Do you see what we forgot? In addition to the 10 seconds that it's going to take to actually send it, we also have to add on 500 milliseconds just to create the connection. When we got to pay that regardless of how many bits we're going to send. So that would really be 10.5 seconds to do the whole thing. Now, packet switching, for one, eliminates that bandwidth waste by sending it at full speed. it doesn't have this dedicated allocation of resources, so it's always shared. And also, there's no reservation overhead. You don't have to wait that connection setup time. You just send. That's shown here. Of course, there are trade-offs with anything, and the trade-offs here, if we think about the disadvantages, are what happens if you're trying to send more than can actually be sent. You haven't reserved it ahead of time, so it might happen. Yeah, you're just gonna have to wait. This is congestion, right? You've driven on an interstate where there are too many cars to be driving at that moment, and that means everybody slows down. So we have several issues here where we will slow down the speeds, or we may even lose packets if there's too many to be stored and they have to be dropped. Right, buffering may help with this, but there's a limit to how much you can store as well. Here's an example of packet switching, which is also called statistical multiplexing. The idea here is that if you were to send packets out from A and B, and they're going out to other hosts on this network, you can see that A and B have different colors of packets. Imagine that A and B are sending on this network that can support 100 megabits per second, but the output link here only is at 1.5 megabits per second. So it's possible that there may be bursts where you have a lot more packets, and it may even be, it looks like here that host A is sending at a faster speed than host B, like twice as often, and that's why there's more dark blues than light blues. Over time, we can imagine though that they get queued here. That's one thing that's shown. If there's too many at this moment to send, then they'll have to wait in a line. If, however, over the long term, if we can, if they kind of stop sending for a little while, then the queue has a chance to work through itself and send. And over time, these will be sent in a kind of statistically in the same way that they were sent in, right? Where we still got, it's like we're splitting the link, but now we split it 2/3, 1/3, maybe. If A was sending twice as much as B. And we did this without having to reserve time slots like we did in a circuit switch network. Okay, this last example that we're going to do today is as follows. Let's imagine we have this scenario where we've got two computers. The sender is sending a file that's L bits long. Right, and L is 7.5 megabits. So there's this file, 7.5 megabits. The speed between each router, that's what the speed of each link, and those purple things are routers, is 1.5 megabits per second. So the question is, what's the total transmission delay over this system? Well, let's work on that first piece first. How long does it take to get from the sender to the first router? Right, so we've got over this first piece, it can send at a speed of 1.5 megabits per second, and L is 7.5 megabits long. So how much time will it take to transfer that? How'd you get that? Does that make sense to you? So we've got megabits, which is our length, divided by the speed at which we can send. Megabits divided by megabits per second is going to be something that's in seconds. It's going to be 5 seconds. So it takes 5 seconds to do that piece. How long will it take to do this piece? From R1 to R2, I'm going to call it. And this one? Right. Well, if the speed at each one is 1.5 megabits per second, and we've got L, then why doesn't it take 5 seconds to go over all of it. Why does it take 3 times that? Right. So this is because of this store and forward property of routers. It's got to receive the whole packet, work and send the whole packet. So that's going to increase our effective speed. So as we conclude our discussion on types of switching, I wanted to try to connect this to the real world, the world that we live in, and think about what would be human analogies of circuit switching and packet switching. Can anybody think of anything that you think was sort of the way the reserved resource allocation approach to circuit switching? Let me throw one out. I think that maybe, I don't know all the ins and outs of the hotel industry, but it might be like hotel reservations. When you call ahead to a hotel and you say, hey, I need a room tonight, and you give them your credit card, and then they usually put some hold on your credit card for some amount of money. And then when you go there, like you may be like 3 hours away and not close to the hotel, but when you get there, you are guaranteed to have a room in that hotel that night. Yeah? So that's kind of like circuit switching, where you have to set up stuff ahead of time, you reserve the resources, but when you need it, it is there for you. And you got a solid hold on those resources. Okay? Now, on the other hand, packet switching is more of an on-demand resource allocation. Remember that packet switching, we get to send at the full speed, but we might run into congestion if a lot of people are after that resource. I compare this to an airline reservation system. You know what airlines do? It's a little tricksy. Airlines will sell more seats than they have. Have you heard about this? Right? And why do they do that? Right, they expect people to cancel, and they still want to have a full airplane because that's when they make the most profits. I mean, that's the best efficiency for them. And I think if more people show up than actually they have seats for, they'll bump you, right? But they'll pay you to be bumped, right? I'm not making this up, right? So this is their system of dealing with this allocating resources. They'll oversell. And I think that's sort of like packet switching, where, right, everything is really fine and good as long as you have too many people or too many requests for resources, right, which is when congestion happens in a packet switch network. Okay, so there's our human analogies. Let's do a comparison looking more at the technical side. Imagine that we had a link that runs at 1 megabit per second, and each user, we have n users, let's imagine some variable n, and each user uses 100 kilobits per second when they're active, but they're only active 10% of the time. All right, that's the setup. So the first question is, if this is a circuit switch network, how many users can we support? We've got a 1 megabit per second link, and each user uses 10 kilobits per second when they're active, and they're active 10% of the time. The circuit switching is actually the easier problem to solve here. So how many users can we support if we're circuit switching this environment? 10. And why is that? How'd you get 10? Right. So you divided 1 megabit by 100 kilobits, and that means 10. The 10% of the active 10% of the time doesn't matter. You're guaranteed, if you're a user in this system, to get your full amount if you need it. If you don't need it, then it's just wasted. So the circuit switched approach would support 10 users. The packet switched approach is quite a bit more complicated because we have this probability going on. So if you're into probability and running those kinds of the math that probability does, what you'll find is that even if you have 35 users, the probability that more than 10 of them are active at the same time, if they each have a 10% probability of being active, is less than 0.0004 or 0.04%. So this is good, right? This says even we could probably, most likely, we could support 35 users and they wouldn't run into each other. They wouldn't overwhelm the maximum resource that we have. So you see how that's, in a lightly loaded network, the packet switched approach is much more efficient, much better use of resources. It's going to support more users. All right. As we conclude this discussion of packet switching versus circuit switching, we want to ask, well, is packet switching just this ultimate slam dunk winner? Right? And the answer to this question is almost always no, right? There's always got to be a catch, and let's understand what the catch is. Packet switching is great if the data is very bursty. You know, it's fast and then it's slow. It's simpler, there's no call setup, we could send it to full speed, but if we are pretty much very high speed all the time, we're going to get congestion, and congestion is bad. If we're very full, if we are almost always utilizing all the resources that are out there, all the bandwidth that's available, we're going to have congestion, and that's going to lead to packet delay and possibly packet loss. So there's this trade-off going on. Also, something interesting is there are often times when we need to provide circuit-like behavior over a packet switch network. For example, if you need to send video, like real-time video over a packet switch network, then you kind of do care about having a reserved amount of bandwidth because your video is going to look bad if you can't maintain this constant rate of transfer. So this is audio-visual streaming kind of apps. This is important, and in our book, actually, Chapter 7 talks about a lot of issues related to this, multimedia networks, and the kinds of things you need to do to take care of that. So really, both of these approaches have their have uses, have strengths that we want to have, that we want to utilize. Okay, the last thing in this section tries to give us some insight into the structure of the internet. How is the internet, this really big thing, the internet, how is it structured? It's super complex. The book describes it as a network of networks, and I think that's a very good description. You know, when we access the internet, we typically only interact with, that is, pay money to, kind of this first hop, the access ISP, whether that's your cable company or your phone company, right, like AT&T or Charter. Those are the access ISPs, but that's not really who's running the internet. There's a lot more pieces involved than just that. It's a very complex multi-tier architecture, and the book takes a really interesting approach to explain this that's sort of iterative. So we're going to kind of start out simple and then make it more complicated and more complicated and more complicated until we have a truer picture of the internet. Also note the book makes the good point that the current structure of the internet was driven by economics and national policies. So it's not just about technical kinds of things, the reason why it is the way it is, but about money and business motives and national interests. Okay, so we've got all of these access networks, right, that people are connecting to, end users are connecting to. How do we connect them to each other? Yeah, if I want to be able to do much of anything on the internet, I need to be able to connect to servers that are not on my little access network. Well, we could connect all of these access networks to each other. There's a problem with that. If we connect everybody to everybody else, that's an n-squared kind of problem. That's a huge number of connections when you consider how many access networks there are. This doesn't scale. It's not going to be maintainable. It's not going to work. So instead, let's add another tier, another hierarchy. And we can imagine that in the middle here, we're going to add a global internet service provider. Now keep in mind, this is not the way it really works, but we're doing this just to help us think about it. So imagine instead of that, we have this. We have this global ISP that has some really fast links, it has some really fast routers that route among itself, so that this access network up here can go through this router, this router, this router, this router, this router, to get down here to this access network and some computer in it. Okay? So the global ISP is helping us out by maintaining another layer of structure. And having some, it's going to invest some money in super fast connections and super fast routers. It's got to make up that money. How's it going to make up the money? It's going to charge the access networks to connect to it. Yeah? All right, so that's kind of the money payoff. So these two customer and provider ISPs are going to have an economic agreement to allow them to connect with each other. All right, well, let's think, if this one global ISP can make money doing this, then there'll be a competitor, right? There'll be multiple ISPs that are kind of like global, these top tier ISPs that are competing for everybody's business. In this case, we have 3 of these. Now these tier 1 ISPs, though, are not that useful if they don't connect with each other, right? Because in this case, ISP C connects all of these access networks together, so they can all talk to each other, but they can't talk to anybody in A or B. That's no good, right? So we have to connect to each other. Now, how and why are they going to connect to each other? They'll connect, but there's going to have to be some mutual benefit involved. So how are we going to interconnect these guys? Well, often what will happen if these guys are sort of at the same level is they do this thing called peering, where they connect to each other, they agree to talk to each other and share kind of connections equally. So I can send traffic to you, you send traffic to me in an equal kind of way. Another approach to this problem is that there are kind of these third-party people that run an internet exchange point where multiple tier 1 ISPs will link together and share data among themselves at this place. They'll kind of link up at this at the IXPs. All right, let's add on another level here. Often there will be regional networks that will connect multiple access networks and further kind of create another level, another hierarchy where we can get easy, faster, cheaper sharing among these computers if they actually just need to talk to each other. They don't have to go all the way up to the top level and come back down again. But if you need to get somewhere more global or somewhere further away, you'd have to go through your tier 1. And then lastly, there are these things called content provider networks. So these are some big companies like Google, Microsoft, Akamai, who run their own network and are trying to basically, these companies are so big that they can run their own servers, they can connect their content to users either more, they can get their content closer to the users, so it's faster for the users, and also it's cheaper for these people to run their own networks than to pay for to connect to a tier 1 or tier 2 ISP. Make sense? So if Google, instead of Google paying a bunch of money to send their data over tier 1 and tier 2 ISPs and to connect to a bunch, because they're going to have to send a lot of data, Google actually just buys their own networks and then connects those networks to the users. Let me show you one more diagram here. Kind of imagine at the top level we've got these tier 1 ISPs and content delivery networks like Google, which may connect to tier 1 ISPs, but they may also connect directly to access ISPs. So that's going to give you very fast access, very good service on those, and it's going to be cheaper for Google because they don't have to pay somebody to do that when they can afford to do it themselves. They're also going to connect to the IXPs and possibly the regional ISPs as well. So Google data centers may do this. If you check out your book, they have a really interesting explanation of this. I know this is a very quick, high-level overview of something incredibly complex, and I'm definitely not an expert in it. But check out the the description in the book if you want more. There's also an interesting discussion of this in Chapter 7. There's a little blurb. I think it's 7.2.4, if you want to look at that in the book, that explains how Google does this, how their data centers support this kind of content delivery. All right, so what we've seen in this 1.3, we've talked about circuit switching and packet switching. We talked about the structure of the global internet as a network of networks. Do y'all have any questions? All right.